Hello, so we're going to have a look at some more differentiation today. So it's going to be chapter 12.4 as I've labelled it on the notes. Differentiation, so using the main textbook, which is the blue Algebra 1. So let's get cracking. You know how this begins. We're going to have a look at 4 questions to get you warmed up, which are here. So what I want you to do first of all is to try these questions. So pause the video, write them down and then try to attempt them yourselves. Once you've done that, what we need to do is then have a look and see if you've got them right. So if you've got the printout, great. Pause this video and attempt them. Then we're going to have a look at them for solutions as a class. So without further ado, let's have a look at some of the solutions to these warm-ups. So question 1, what we've got here is a curve, y equals a quarter x, where x can't be equal to 0. We need to find the gradient of c at the point A, where x is a quarter and y is 1, and that's going to lie on the curve as we're told. First of all, what we need to do, we need to rewrite this in a nicer, more manageable form. We need to write this as y equals 1 quarter x to the power minus 1, because 1 over x is the same as saying it's x to the power minus 1. So we can now differentiate this. So dy over dx, which is the same as saying f dashed of x, just a different way of writing the gradient function. The power of x is going to come to the front, so the quarter is going to be multiplied by the minus 1 to give us minus a quarter. They're going to have x, and the power of x here is going to drop by 1. So minus 1 minus another 1 gives us minus 2. And so this will tell us what the gradient is on the curve for any value of x. So here we can just substitute x being a quarter into this expression. So therefore the gradient when x is a quarter is going to be minus 1 quarter multiplied by a quarter to the power minus 2. And so if we try this on the calculator first of all, so type in minus 1 quarter multiplied by 1 quarter to the power minus 2. Let's see what that gives us. We get for this minus 4. Now, if you missed it the other day, I'm going to show you how you could do this on the ClassWiz without doing much legwork at all yourself. If the question will allow you to do that in the exam, you may as well take full use of the power of your calculator. There's no telling if you can do or not, but it's worth knowing this method I'm going to show you now anyway, just as a double check of your manual working, if nothing else. So what we're going to do is press Shift and then the integral button below the menu. And we type in the initial function before it gets differentiated. So our function here is 1 over 4x. So type it in as it is. And we want to evaluate this derivative, d by dx, where x is 1 quarter. And so this line followed by the x just means where x is whatever we want it to be. So we're trying to find the gradient when x is a quarter. Type in a quarter here, press equals, and what do you know? We get exactly the same gradient as what we did using the basic method. So that's a very powerful tool to know. Question 2. We've got a straight line with a gradient listed as m, which passes through the points A and B. So we just need to show that the equation of a straight line can be written in this form here. So what I'm going to suggest we do is just to sketch on a straight line, then label in 2 points on this line. So we're going to label here below, I'm going to say that's going to be A, and let's call A x1, y1. Then up here we're going to put B, which is just generally x, comma, y. And so using the definition of a gradient, for gradient m just equals the change in y between these 2 points divided by the change in x. And so if we just think about this in simple terms, the change in y is just the distance between the y value at b and the y value at a. And so this is just going to be y take y1. So at the top we're going to have y minus y1. At the bottom, the change in x, we're just going to have this value of x over here, which is just x, subtract the value of x over here, which is x minus x1. So m equals the change in y divided by the change in x. So what we can do here, we can multiply this equation through by the denominator x minus x1. So if we multiply both the left and the right by x minus x1, we then get that y minus y1 equals the gradient m multiplied by x minus x1 as required. And so we've proven this form of the equation of a straight line just by using a little sketch. Question 3. A straight line L1 has equation y minus 3x equals 2. Find the equation of the straight line perpendicular to L1 passing through 1, 5. And so first of all, I'd suggest to rewrite L1 in the standard form y equals mx plus c. So add 3x to both sides, we get y equals 3x plus 2. Then if we're talking about a straight line perpendicular to L1, we know that the gradient of any line perpendicular to L1, gradient of line perpendicular to L1, that's going to have a gradient that will be the negative reciprocal of the gradient of L1. So that's going to be minus 1 over 3. And so now we can employ the equation of the line from question 2. So we can use y minus y1 equals m x minus x1 applied to what we know about a point on this line. And so we know the equation of this line perpendicular to L1 passes through 1 and 5. So it passes through where x is 1 and where y is 5. And so that's our known values of x and y, our x1 and y1. We've also worked out that the gradient of this perpendicular line will have a gradient of minus a third. So the m value for this line we're trying to find is going to be 1/3. So if we then just sub in these values, so y minus 5 equals minus a third brackets x minus 1, because as I've said before, the gradient was minus a third, the known value of x was minus 1, and the known value of y is 5. So we can actually leave it like this because the question didn't state what form to leave the equation of a straight line in. So if you wanted to, of course, you wouldn't have to, you could rewrite this as y equals mx plus c. So if you wanted to just rearrange it to a more familiar form, we could have said it's y equals minus 1/3 x plus 16 over 3. There's a third form as well, but I'll leave you to think about what that third form might be. It's the form ax plus by plus c equals 0. But either one of these will do you. Finally, question 4, just going back to quartiles and medians. Some data is collected and we've got these statistics: Q1 lower quartile, Q2 median, Q3 upper quartile. And one common definition of an outlier is a value that is more than 1.5 times the interquartile range, either above the upper quartile or below the lower quartile. So we're going to need to show here that 2.1 is not an outlier. So first of all, what we need to do is to work out the interquartile range. So for these sets of values, the interquartile range is going to be 1.8 minus 0.5, which is 1.3. So 1.5 multiplied by the interquartile range is just going to be 1.5 multiplied by 1.3, which should give us 1.95. So something which is the third quartile, the upper quartile, plus 1.5 times the interquartile range just means anything which is 1.95 above the upper quartile will be an outlier. So 1.5 interquartile range plus Q3, which is 1.8, that gives us a value of 3.75. But the value we've got here, which is 2.1 is not more than 1.5 times the interquartile range. It's not more than 1.95. Whoops, that was slightly incorrect. Wrong colour. So let's just undo that. So it's not 1.5 times the interquartile range above 1.8 at all. It's actually less than 3.75. So therefore 2.1 is not an outlier. So let's have a look here at tangents and normals. So a tangent to a curve at a point P is just any point on the curve where the gradient of the tangent is the same as the gradient of that instantaneous point on the curve. Whereas a normal to the curve is a line that cuts the curve at point P and is directly perpendicular to the tangent at P. So the normal at a point and the tangent at a point intersect at right angles. Okay, so as you can see here, this is the tangent and this is the normal, and they'll always cross over at right angles. From previous work as well on perpendicular lines, you should remember that if two lines are perpendicular, then the gradient of one is the negative reciprocal of the gradient of the other line. So if I just denote the gradient of a normal as m subscript n, that will be the negative reciprocal of the gradient of a tangent, where I've said the gradient of a tangent is m subscript t. So let's have a look at a worked example on these and see if we can make some sense of them. So question 1, we need to find the equation of the normal to the curve C, where the curve C has equation y equals 1 minus x plus 2 root x. And we need to do that at the point where x is equal to 9. So one thing we need to do is we need to rewrite C with the x's in index form to make them easier to differentiate. And so we've got y equals 1 minus x. Now the square root of x is the same as x to the power of 1/2. Now this is easily differentiable. So what we can do here is just do dy by dx and take each term one at a time. 1 is a constant, that differentiates to 0 and vanishes. Minus x will differentiate to minus 1. This here, 2x to a half, the half comes to the front and multiplies the coefficient of x. So 2 times a half just gives us 1. And the new power of x decreases by 1. So a half minus 1 is minus a half. Therefore, we can now compute what the gradient will be at the point where x is equal to 9. So f dashed, where x is 9, is going to be minus 1 plus 9 to the power of minus a half. So that's just the same as 1 over the square root of 9, which is going to be 1 over 3. So minus 1 plus a third will be minus 2/3. But I'd always strongly suggest you try this with a calculator. Okay, so you should get minus 2/3 for that. Just to quickly recap, yet again, the power of the brilliant ClassWiz. So you can actually do this on a ClassWiz manually by doing shift integral, typing in the function you wish to differentiate. Let's imagine we want it to be super lazy and not rewrite the initial equation into this form. So just take it in this form. We've got 1 minus alpha x plus 2 root alpha x. And we want to find the gradient of that, where x is equal to 9. Almost forgot myself. We get there minus 0.6 recurring. For some reason it gives it as a decimal. That's the same as minus 2/3. So that's the gradient of the tangent. Gradient of the tangent when f is 9. However, we want the equation of the normal. So if I just give myself a bit more space here, so I'm not going to scroll down loads. So therefore, the gradient of the normal when x is equal to 9 will be the negative reciprocal of the tangent. So it'll be minus 1 over this. So it's going to be minus 1 over minus 2/3. So it's going to be 3 over 2. So what we need to do here as well is to be thinking of the value of y. So we know the value of x is 9. We can also work out the value of y on this curve by substituting in where x is equal to 9. So also, when x equals 9, on the curve C, we've got that y equals 1 minus 9 plus 2 lots of the square root of 9. And this is going to equal minus 2. And so y is going to equal minus 2. And so what we have here is we've actually worked out the x-coordinate and the y-coordinate at this normal. So x is 9 and y is minus 2. So now we can employ the standard form for a straight line when we know a certain point on the straight line. So like before, we can use y minus y1 equals a gradient multiplied by x minus x1. Only now in this case, we know that the x-coordinate, the known one, is 9, and the known y-coordinate is going to be minus 2. And the gradient, of course, m, is 3 over 2. And so if we plug these values in, what we're going to get here is y minus minus 2 equals m, which is 3 over 2, then x minus x1, which is 9. So just plugging in the values which we know. So the gradient is 3 over 2. The known x-coordinate is going to be 9. And we just calculated earlier the y-coordinate is minus 2. So what we're going to have here is y minus minus 2. So y plus 2 equals 3 over 2 brackets x minus 9. Now the question doesn't specify what form to leave the equation of the straight line in, so this will do for our final answer. I'll just show you a couple of alternatives which you could have though, however, if you wanted to. So you could have had, in the standard form, y equals mx plus c, we could have had y equals 3 over 2x, and then the c term would have been minus 31 over 2. Or we could have had it in the form ax plus by plus c equals 0. And that would have been 3x minus 2y minus 31 equals 0. And so I just suggest to leave it in the form of underlined in red, as that's simpler. We can save yourself some time, so you don't need to rearrange into a different format. Now, question 2 is actually a previous exam style question on this. So this is understandably slightly more challenging, but we're going to talk it through step by step. So first of all, we've got this equation and we need to show that the point P lies on C. And so what I'm going to suggest we do first of all is to just simply substitute in the value of x into this curve. So we're told that the value of x at P is 2. And so if we sub in x is 2 into this equation of a curve, we can see what drops out. And if it's right, then when x is 2, y should drop out as being 7. So for part A, we're just going to sub in where x is 2. We then get y equals 2/3, sorry, not 2/3, 2 to the power 3, minus 2 times 2 squared, minus x, so minus 2, plus 9. So again, just to highlight the fact, literally highlight, that we're just using the value where x is 2. So if we just bang that into our calculator, so go back to normal mode, menu 1, so 2 to the power 3, minus 2 times 2 squared, minus 2 plus 9, we get 7. So therefore that shows when x is 2, y is 7, therefore the point 27, the point P, must be on the curve. So therefore P, which is 2, 7, must lie on the curve C. Oops, my mistake. So that's part A. Part B, it says find the equation of the tangent to C at P. Given your answer in the form y equals mx plus c, where m and c are constants. So let's just give myself a bit more space here in which to write down the solution to part B. So for part B, what we need to do here is to work out the tangent to C at P. So we're going to need to differentiate this function. And so dy by dx, let's take it one term at a time. The gradient function, differentiate x cubed, bring the power down to the front. The power of x now decreases by 1, so the 3 becomes a 2. Here, this power comes to the front and multiplies any coefficient which was already there. So we're going to have minus 2 times 2, which is 4. The power of x is going to decrease by 1. 2 minus 1, we just have x to the power 1. Minus x, so that would be power 1. If 1 comes to the front, we now have x to the power 0, which effectively vanishes. Anything to the power 0 is just 1. Minus 1 times 1, we just get left with this. Any constant disappears altogether. And so this is the gradient function for part B. So next what we need to be doing is considering the gradient of the tangent at P. So at P, the x value at P is 2. So what we need to do here is to work out the gradient when x is 2. So therefore, what's f dashed of 2 going to be? Well, that's going to be 3 times 2 squared minus 4 times 2 minus 1. Again, just using the fact that we know what the value of x is. We know the value of x here is 2. So if we just type this into our calculator, or otherwise, 3 times 2 squared is 12, minus 8 is going to be 4, minus 1 gives us 3. So the gradient of a tangent is 3. We also know, because this tangent is at P, that P itself is going to be on that tangent. P is where the tangent just scrapes the curve C. So again, we can use the old trusted y minus y1 equals x minus x1 form of the equation of a straight line. So y minus y1, where y is the known coordinate of y, was 7. So y minus 7 equals a gradient of this tangent, which we worked out is 3, then x minus the known x coordinate, which of course is 2. So what we can do here is now just expand, rearrange, and get it into the form y equals mx plus c. So y minus 7 equals 3x minus 6, and therefore y is going to equal 3x plus 1. And that's the equation of the tangent to C at the point P. I've lost the tail of the y, so let's just do that. There we go. So y equals 3x plus 1. Part C is definitely the hardest part of it. And so what I'm going to do now is I'm just going to clear all this off so that we can work out C together. So make sure you've got a note of this. Pause the video now if you need to copy this out. I'm going to clear all this away. So bye-bye. And you as well. Get lost. Respectfully get lost. Part C, show that the x-coordinate of Q is 1/3 brackets 2 plus root 6, where point Q is also on C, and that the tangent to C at point Q is perpendicular to the tangent to C at P. A bit of a mouthful. So let's just think about this step by step. Well, we know for definite that the gradient of a tangent at Q is perpendicular to the tangent at P. So let's just put this down in some plain English. So the tangent at Q is perpendicular. So just say that's perpendicular to the tangent at P. I'm just trying to get this question written in a way which just makes a bit more sense, because sometimes the wording can throw you off. Tangent at Q is perpendicular to the tangent at this point P. So just, if you can, think about what we know about the gradients of perpendicular lines. If two lines are perpendicular, the gradient of one is the negative reciprocal of the gradient of the other. Okay, so we now know that the gradient of a tangent at Q will be the negative reciprocal of the gradient of a tangent at P. So we can get this as our starting point. So the gradient of a tangent at Q is going to be the negative reciprocal of the gradient of a tangent at P. Now from part B, we had that y equaled 3x plus 1 for the tangent at P. So the gradient of the tangent at P was 3, therefore the gradient of the tangent at Q will be minus 1 over 3. It's going to be negative 1/3. Okay, but we also know from part B, so also from part B, we worked out the gradient function. So we worked out that dy by dx, the gradient at any point on the curve, was going to be 3x squared minus 4x minus 1. And so this tells us the gradient of a tangent at any point where we know the value of x. And so we're told, well not told, sorry, we've worked out the gradient of a tangent at Q is minus 1/3. And so what this is saying here is that the gradient function at Q, the gradient at Q is the gradient of a tangent at Q, which is minus 1/3. And so we can actually substitute in that the gradient at Q is minus 1/3. So we can substitute minus 1/3 into dy by dx. We can then solve for what the value of x needs to be to give us a gradient of minus 1/3. So let's do that now. So therefore minus 1/3 equals 3x squared minus 4x minus 1. So get this all to one side of the equation. We have 3x squared minus 4x, add 1/3 to both sides, we'd have minus 2/3 equals 0. Now be careful, it does say to show that the x-coordinate of q is a third, brackets 2 plus root 6. So be very hesitant to just bang in numbers onto your calculator and just skip to this end result here. You need to show it step by step. So this is a slightly awkward quadratic. Let's use the formula, and then we can simplify the formula and show the result clearly. So therefore we're going to have that x equals minus b, as it were. So minus 4, which is 4, plus or minus the square root of b squared minus 4ac, all over 2a, as you should remember from GCSE and earlier work this year. So b squared is going to be minus 4 all squared, which of course is 16. You could leave it here as 4 squared and simplify later. That would be fine as well. Then minus 4 times a, which is 3, times c, which is minus 2/3. Be sure to include the minus 2/3 in here. All divided by 2 lots of a, which is 2 times 3, which is 6. So we then have 4 plus or minus the square root of, well, let's work this out. So on a calculator, I'd suggest doing this. 16 minus 4, just move this over here so you can see what we're doing. So for third, 16 minus 4 times 3 times negative 2/3 gives us 24. All of that over 6. Now root 24 is actually the same as root 4 times root 6, and so I can rewrite this as 2 root 6. 4 plus or minus 2 root 6, all over 6. Scroll down slightly. Even coefficient, even denominator, so that can be rewritten as 2 plus or minus root 6 over 3. However, we now need to think about why we've not got the same as this. It's almost the same, but we've got plus or minus. Why is this just a plus? Be careful to read the question carefully every single time. So if we go back to the start of this question, look how x was defined. X was defined as being greater than 0, and that's the key. So if we now just go back and state clearly, but since x is greater than 0, we need to reject this negative third part. So the solution is just 2 plus root 6 over 3, which you can rewrite as just simply 1/3, just sectioning out of the denominator, 2 plus root 6 as required. So a bit of a meatier question, but hopefully, as you see, if we take it step by step and don't get too flustered or panicked, we can crack these as well. Okay everyone, so as per usual, we need to just consolidate these skills. If you could turn to page 269 in your books, exercise 12F, try all the questions from this exercise if you can do, please. Okay, as I've said before, differentiation underpins an awful lot in this year 12 maths course and year 13 as well, so to master it is going to be a key to success. So have a go at those. Any questions you're struggling at, drop me an email or leave a comment. So good luck with those questions, and I'll be in touch with another video soon. Thanks for listening.